everyone. Welcome to Chemistry in a Minute. I'm Mr. Saucedo, and we're working our way through Zumdahl, the 7th edition. We're on Chapter 9 right now, which is all about covalent bonding. There's a ton of stuff in the book that is not relevant to the AP Chemistry exam, so we're going to be skipping some things. But keep in mind that we're also going to be focusing on something that I thought was a little weird for them to leave to Chapter 9. So there's a little bit of stuff at the end here that's going to probably be a little bit of a flashback to something we've done in a previous unit. So let's start with section 9.1. So we've got hybridization and the localized electron model. So first things first, let's draw our orbital diagram for carbon. Okay, so remember, this is already a flashback for us, isn't it? We're drawing an orbital diagram for carbon. We need to know how many electrons carbon has, and then we just fill them in sequentially. So our 1s becomes full, our 2s becomes full, and we're left with 2 extra electrons in our 2p orbital. That's how you draw the orbital diagram for the ground state of carbon. How many valence electrons does carbon have? It has 4. A lot of times people forget, but these and these are valence electrons. The core electrons are the 1s for carbon, but because these are technically the same energy level, they're at the 2 for the 2 level, each of these is a valence electron. So it has 4 valence electrons, which explains why when we draw the Lewis dot structure for just carbon by itself, we have 4 dots around it. Okay, now, what shape does an s orbital have? Again, another flashback. And what shape does a p orbital have? So s orbitals have the following shapes, right? They're basically just spheres. A 1s has a tighter sphere than a 2s does. And then a 3s, again, would have even a larger sphere than a 2s would, because remember, every time we gain an extra principal quantum number here, we're getting further and further away from the nucleus, generally speaking, right? And what about the p orbitals? So remember, the p orbitals have this dumbbell shape, and they come in 3 varieties, which is why we represent it with 3 boxes. So again, thinking back to the previous slide with our orbital diagram, the reason why we had 3 boxes representing the p orbital there for the 2p level was because there are actually 3 different p orbitals. You have the xp orbital, or px, you have the z, and you have the y. So you can think about it 3-dimensionally. One is horizontal, one is vertical, and one is coming out towards the screen. Okay, why are we talking about all of this? Well, we just talked about atoms right now, just carbon. But what happens when carbon is forming a molecule? So here's how this kind of works and why this unit is important. What happens to those electron orbitals when you're forming something like a molecule? What if I wanted to make methane, CH4? Or what if I wanted to make, I don't know, ethane, C2H6? What happens to the bonding and what happens to the orbitals when I make a molecule? So the truth of the matter is the orbitals that we're talking about become hybridized. So section 9.1 is all about hybridization. And what does hybridization mean? Basically, it means the orbitals become mixed. They become a mixture of s orbital and p orbital. So they actually become a hybrid of both. And that's super important because, again, looking back at a previous Zumdahl chapter that we already covered, it explains those Vesper shapes like tetrahedral, trigonal, planar, etc. So let's actually look at what happens to our carbon when we form these hybridized orbitals. So let's pretend we're making 4 single bonds. This is what actually happens to our orbital diagram. So notice the 1s didn't change. They're still core electrons. But look at what happened to our 2s and our 2p orbital. Instead of having a separate 2s and a separate 2p, they basically became merged together to form this hybrid. Okay, so we still fill it in the same way, but because now all of these boxes that follow are hybridized, they all have the same exact energy, which means that when we draw our 4 little dots around our carbon when we're drawing the Lewis dot structure, what we're really saying is that this is occurring. They're all of equal. Each of those electrons that are going around the carbon in that molecule are of equal energy. And that's what hybridization is all about. And you might think, well, what do they look like and all of that stuff? We'll get to it. Okay, so yes, the shape has changed and the properties a little bit have changed, right? So what do we call these hybridized orbitals? Well, when we have four single bonds like this, we call it an sp3 hybrid orbital. Notice that it's kind of giving you a clue that when you say sp3, that you have an s, that's one s. And when I say one s, I don't mean the core electron. I'm saying there is a single s orbital. And you have 3p orbitals. Again, I'm not saying that we're in the 3p level. I'm saying that we have triple the amount of p orbitals. So in reality, the sp3 hybrid orbital is about 75% p orbital and about 25% s orbital. And notice that the carbon, again, right here, has 4 spots to accept electrons in order to form its 4 single bonds in its molecule. Okay? And so that is the importance of hybridization. But let's actually look at this, right? So if we're looking at the energy levels here, right? 2s has less energy than 2p does, right? But when they're hybridized, they all have the same energy here. So notice, though, that the energy here, because it's 75% p orbital, it's closer in energy to the 2p than it is to the 2s. And now let's look at how that's formed. So when we mix together an s orbital and 3p orbitals, what we get is a shape that looks like this. So really, you have a much greater likelihood of finding your electrons that are forming your bonds around these little corners here. And what does this kind of weird sp3 hybridization of orbitals look like to you? It should resemble something that we've already talked about. Believe it or not, each of these little nodes, which I guess I probably shouldn't call them nodes because they have a totally different definition. These points, I'll call them points, are all 109.5 degrees from one another. And so what does that remind you of? Well, that should remind you of a good old tetrahedral shape. So if you're wondering why that Vesper shape actually exists, it's because the orbitals themselves in that carbon have dictated that everything is 109.5 degrees from itself. Now, let's talk about something as a little side note. So I don't like the order that the book does this, so I'm going to talk about this now. But what is a sigma bond? So we just talked about what an sp3 hybridization means. Now let's talk about a sigma bond. A sigma bond is just what happens when we are looking at electron pairs that are shared in a straight line between two atoms. Okay? Each single bond, every time you see a single bond or have drawn a single bond in a Lewis dot structure, what you are actually drawing is called a sigma bond. Okay, it's just a nice little piece of nomenclature for what it's called. Now, why am I telling you this? Well, we're going to use some of that information in a little bit. So what is the shape of a methane molecule and what are the bond angles? All right, we can do that, right? So we draw our methane molecule, CH4, like this. It's a tetrahedral shape. Even though I drew it flat, you know that in reality, I have one hydrogen pointing this way, one hydrogen pointing that way. One is going back and one is going forward. What's the bond angle? It's 109.5 degrees. Again, we already know that. Now, what if I ask you, what is the hybridization of this carbon right here in the middle? Well, it's sp3 hybridized. If it has a tetrahedral shape, it must be sp3 hybridized. And then last but not least, how many sigma bonds are actually present? Okay, well, we have a single bond here, a single bond here, single bond here, and a single bond here. That means we have 4 sigma bonds in this picture, one between each of the hydrogen and carbon bonds. Okay, now what does that actually look like if we were to look at it in a hybridization kind of way? So this is our carbon. These are our hydrogens. They're all, again, 109.5 degrees from each other. Notice that our orbitals are sp3 hybridized for the carbon. And notice that the orbitals for the hydrogens are still just 1s, because that's what hydrogen is. It's just 1s, right? And notice that we have our little arrows. So we're actually pointing out the fact that we are forming a bond by filling in that orbital diagram. And now we have our methane picture. All right, now what about ethylene? Okay, C2H4. What if I asked you to draw that? So it would look something like this. Now we have a double bond. What is the shape? Well, each carbon is trigonal planar. You can see I have 120 degree angle between each one of these, right? So here's the main question now. We just talked about sp3 hybridization. Why can't ethylene be sp3 hybridized? The answer is pretty simple. sp3 orbitals have to be tetrahedral, and what we have is a 120-degree shape here. So it can't be sp3 hybridized. There must be another form of hybridization that explains it, and there is. It's called sp2 hybridization. So now we have an s orbital and two p orbitals. So again, we have about a third of its nature is from the s, and about 2/3 of its nature is from the p orbital. So it does give a trigonal planar arrangement. And something kind of important, notice that we are missing a p orbital here. We have one s and we have two p's, but there is still that, third shape. So what happens to that other p orbital? Well, we call that other p orbital an unhybridized orbital. And this becomes important because the unhybridized orbital is perpendicular to the sp2 plane. So why is that important? Well, we just talked about a sigma bond. There is something called a pi bond. A pi bond is what happens when we actually form something like a double or a triple bond. And it occurs when we share electron pairs or an electron pair in the space above or below a sigma bond. And you guessed it, it uses the unhybridized p orbitals in order to do that. So if we're looking at sp2, notice that again, because it is mostly p in nature and not, not quite as much s, that the sp2 orbitals are a little bit lower in energy than the sp3 would be. And notice that we still have that 2p unhybridized orbital that's, left over as a little orbital box. So why is that important? Well, again, when we're looking at the picture, this is what it would look like. It looks very similar to the sp3, but we only have three little kind of, again, I want to say the word node, 3 points. And so notice this should look familiar. We have 120 degrees between everything. That is the definition of a trigonal planar shape. So whenever we see a trigonal planar shape, we're talking about, again, something that is sp2 hybridized. All right. Now, what does the bonding actually look like in ethylene? Well, we've got our double bond occurring between the carbons. And so the way we make that happen is we have a sigma bond, one sigma bond, and then we have a pi bond that is also occurring. And it might look like, okay, the pi bond, there's room for two bonds here. That's why you can have a triple bond. In reality, what actually happens are the electrons can exist here, or they can exist here. They can move between both of these equally. And so again, like it says here in the little note, it is important to note that a double bond is formed from a sigma bond, just like before. But now we also have this space above or below that can be used in order to form another type of bond, and we call that a pi bond. And literally what it is it's just p orbitals that are overlapping each other. And again, that's kind of how a pi bond is formed. So what's the hybridization between our atoms here of carbon? Well, it's sp2 hybridized. How many sigma bonds are present? I don't want you to accidentally make a mistake here. There are 5. You have single bonds between the carbon and the hydrogen, so there are 4 from that. And remember, in order to form a double bond, it takes 1 sigma bond. So there are actually 5 sigma bonds in the picture. How many pi bonds are present? Just 1. That's forming the other bond that forms our double bond between the carbon and the other carbon. All right, now let's do CO2. We know CO2 has a linear shape to it. We know its bond angle is 180 degrees. Again, we run into a problem that doesn't explain the hybridization of carbon in this situation, right? It can't be sp3 because that would be tetrahedral. Can't be sp2, that would be trigonal planar. So what is actually going on? Well, you guessed it, there's another form of hybridization called an sp hybridization. That is made up of a single s orbital and one single p orbital, and we have an even 50-50 split of s and p. So it is equally split between both, right? It does give you a linear arrangement of atomic orbitals, and now we have 2 p orbitals that are not being used and are unhybridized. One of the orbitals is above and below the sigma bond, the other is in front or behind the sigma bond. So again, if you're picturing it above and below or in front and behind. So if we're looking at it, notice that the sp orbital is directly between the 2p and the 2s, and we still have 2 empty boxes that are unhybridized above it. Okay, so what does it look like? Well, very similar, except now we have a 180-degree angle between both of our orbitals. So it should look familiar to you because it forms a 180-degree difference, which is a linear shape. All right. Now, what does it actually look like? It looks pretty crazy, right? So we have our carbons here. We have a sigma bond between them. We have a pi bond that's forming. Again, we have two different locations for that pi bond. We have one that's forward and backwards. We have one that's up and down. And then the oxygens are obviously way more complicated than a hydrogen looks. So their orbitals are overlapping also in crazy ways, but we still just have one overlap here between their p orbitals. Okay, what's the hybridization of the carbon in CO2? It's sp. How many sigma bonds are there? 2. We have a sigma bond and a sigma bond. How many pi bonds are there, though? There are also 2. We have a pi bond and a pi bond. So what you need to be able to do, basically, is to identify this type of information. So if it's sp, it's made up of an s orbital, 3 p orbitals, for a total of 4 hybrid orbitals. There are no unhybridized orbitals, and it's a tetrahedral shape. If it's sp, again, it's made up of 1 s and 2 p's. We have 3 hybrid orbitals and 1 unhybridized orbital, trigonal planar shape. Last but not least, we have an sp hybridization, which is made up of 1s and 1p orbital, 2 hybrid orbitals total, 2 unhybridized orbitals total for a linear shape. Now you might think, hey, the book goes over some other d orbital stuff. Well, that's not on the AP exam, so you don't need to worry about d orbital interactions here. In fact, some of that is a little bit hazy and not entirely understood. So rather than teach you something incorrect that might get fixed in a textbook years from now, they'd rather just go with the stuff that we actually do know with almost 100% certainty, which is about hybridization up to the sp3 level. Now, something else, because we didn't have any examples of triple bonds here, so I want to make sure we also know this. Single bonds are made up of sigma bonds, and that's it. A double bond is made up of a sigma and a pi bond, and you probably already guessed this, but just in case you didn't, I wanted to make it explicit. A triple bond is still made up of a sigma bond and also made up of 2 pi bonds. All right, let's do a concept check. What if we wanted to draw HCN? We wanted to draw hydrogen cyanide's structure. What is the hybrid orbital that's being used? And then let's show all of the bonds and label our sigma and pi bonds. Well, let's draw. It looks something like this. I don't know why the little, dots got cut off a little bit, but it's just a pair of electrons. That's all it is. So the carbon has a linear shape here, which means it must be sp hybridized. There is a sigma bond here. There is a sigma bond there and 2 pi bonds. All right, last but not least, now we're skipping a lot here, by the way, at the end. Well, the answer came up already. Well, it doesn't matter, who cares? So determine the bond angle and expected hybridization of the following central atoms for each of the following molecules. Well, I gave away that answer already. So NH3, it has a tetrahedral shape to it, right? But one of them is empty, so we call that a trigonal pyramidal shape. But still, the nitrogen is going to be sp3 hybridized. So I wanted to do that one in particular because a lot of times people are like, but NH3 doesn't have a tetrahedral shape. Well, in reality, it does. It's just that, it has 2 electrons. And so since it has a lone pair of electrons on its central atom, we basically have a trigonal pyramidal shape instead. But technically, still hybridized the same. Okay, what about SO2? SO2, 120 degrees, so it must be sp2 hybridized. And again, if you actually draw it, there's going to be a lone pair of electrons on your sulfur. So you might think, okay, well, it's bent. Yeah, but again, if we include our lone pair in our picture, everything's at 120 degrees angle from the lone pair downwards. And so technically, it's still sp2 hybridized. And last but not least, we have silicon dioxide. That has a 180-degree angle, and that's going to be sp hybridized. And again, that's just in general how this process works. Now, we're going to skip a little bit. So we're skipping all the way to section 9.6. I don't know why it does photoelectron spectroscopy here. It should have really done it when we were talking about, drawing orbital diagrams, but it didn't. So we have to talk about it. So what is PES? Well, it can be used to determine the relative energies of electrons in individual atoms and in molecules. Now, on the AP exam, they only care about individual atoms, not necessarily the molecule part. So we're only going to do examples where we're looking at individual atoms. And the way it works is like this. We have a high energy photon that's directed at a sample of an element, and the kinetic energies of the ejected electrons are measured and graphed. And so you end up with a little kind of graph that looks something like this, where you have these little peaks that are going up and down all over the place. So here is what a general one that you might see on like the AP exam looks like. And we're going to talk about what they mean. So notice that we have the binding energy here at the bottom. It tells you how much energy it takes to remove an electron. Notice that the higher energies are on the left for this diagram. The lower energies are on the right for this diagram. Now, that doesn't mean that you won't ever see it flipped before. So be very careful reading the axes of these diagrams. They can be purposefully misleading and tricky, and I've seen it on the AP exam before. So just keep that in mind. Now, what does this tell us? The more binding energy we have, so again, the further on this graph to the left we are, the more difficult it is to remove the electrons. So these are the core electrons that we're talking about here. This little peak represents the core electrons. Now, the less binding energy, the easier it should be to remove the electrons. These are what we term, again, the valence electrons, right? Because it should be easier. It should take less energy to remove a valence electron than to remove a core electron. Now, what about the peaks themselves or the little bumps? Now, the bumps represent the relative amount of electrons that are in each orbital. So the higher the peak, the more electrons that particular orbital possesses. And it is relative. So theoretically, you should be able to look at the peak and then kind of figure out, okay, this goes up to 2, so this must mean that there are, 2, 2, 3, 4, 5. Oh, there are 6 electrons in this level. Like, you should be able to do something like that. But a lot of times it doesn't actually give you the little numbers, and sometimes it doesn't even give you the lines. So it really is just giving you a general idea of where the electrons and how much energy they have in each atom. So like it says, each little peak basically represents an orbital, though. So the height of the bump has to do with how many electrons that orbital has, but the bumps themselves represent the orbitals. So this would be like the 1s, this would be the 2s, this would represent the 2p. So based on my limited interaction with this diagram right now, I would say that, so we have 2 electrons here from the 1s, so that's 1s2. We have 2 electrons here in the 2s, that's 2s2. And then I'd say we have 2p6, so I would say this would most likely be neon. Okay. So what element do you think is represented by the following PES? So again, make sure you always steady yourself with what the binding energy direction of the axes means. And then let's go. All right, so that probably is the 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s. So notice the heights, though. This goes up to here, this goes up to here. So it looks like the 4s is full, because remember, the 1s can only hold 2 electrons. So this would be, most likely in my case, I'd say calcium. Calcium goes up to 4s2. Now, something else that you should be aware of are that sometimes they'll have you compare PESs to each other. So this is lithiums and this is berylliums. And so don't forget something, again, from a previous video that we called the higher effective nuclear charge or a lower effective nuclear charge. So the higher the effective nuclear charge of an atom, the more shifted towards the left the actual graph will be. So lithium has a single little electron, right, in its outer valence shell. Beryllium has 2. As we go across, though, notice that beryllium has a much stronger hold on its electrons because it has a higher effective nuclear charge than lithium does. Also notice that the height is different, that this only has a single electron in its valence shell, whereas this goes up to the 2 because it actually has 2 electrons in its valence shell. And so again, also remember, the more shielding that something has, the lesser the effective nuclear charge will be. Okay, so again, they're kind of opposites. The higher the effective nuclear charge, the more shifted to the left. The more shielded it is, the further to the right it will be instead. All right, so thank you very much. We'll go through chapter 10 in Zumdahl next. So feel free to subscribe and like this video. Thank you very much.